Okay, let's take a look at a phenomenon called degenerate. We're talking about binary trees in this case, but this applies to all trees. Okay. Degenerate binary trees. Okay. So what do we mean by degenerate binary trees? Let's insert the following sequence into an empty binary search tree. Okay, so here we go. So we're going to insert the sequence 19, 4, 12, 10, 6, 7, and 9 into an empty binary search tree. So we'll begin here. We add the 19, and then we're going to add the 4. 4 is less than 19, so we come off to this side, and we add the 4. And now we've got to add the 12. Well, that's less than 19. It's greater than the 4, so we add the 12 at this point. And we'll add the 10 next. It's less than 19. It's greater than 4. It's less than 12. Okay. And then we'll get the 6. Less than 19, greater than 4, less than 12, less than 10. Okay, so the 6 goes over here to the left of 10. And then the 7, okay? So if we trace it all the way back to the root, we'll realize that the 7 belongs here. And finally, we'll add the 9, which is less than 9, less than 19, greater than 4, less than 12, less than 10, greater than 6, greater than 7. So the 9 shows up here. Well, if we take a look at this, this is largely a linked list on its side, right? This is a linear data structure that really is no different than this. 19, 4, 12, 10, 6, 7, and 9. And so even though we have a binary search tree, which is supposed to help us search for items in a more efficient fashion, we still have, in essence, what is a linked list here. And this is called a degenerate tree. And the reason why this happens is that this tree is really completely out of balance. Okay, so we see that this degenerate tree condition can lead to us searching in order n versus order log n, which is what we're promised to get with a binary search tree. And so the question is, how do we take the degenerate tree and put it back into balance? And so there are a few ways to do that. One is to actually take the entire tree and feed it to an algorithm such as the DSW algorithm and have it basically remanipulate the entire tree back into balance. If our data structure is in a rather large tree, this is problematic because we may be manipulating nodes that are largely imbalanced, and yet we're having to look at every one of them. So the question is, can we do this in a simpler manner? Can we do it locally? And it turns out that we can. The things that tend to throw an imbalanced tree out of balance are pretty limited. It's either I insert a node into the tree or I actually remove a node from the tree. That's a rather local operation. And if we can rebalance at the point or in the general neighborhood of where that deletion or that insertion takes place, then we're bound to get better performance. So these are then called self-balancing tree methods, and we will cover one of them. We will cover AVL trees, which are named after the two individuals. It's actually a hyphenated name that you see there. And we will not cover red-black trees, but red-black trees are yet another example of a self-balancing tree algorithm. So what's an AVL tree? An AVL tree is, it's also called an admissible tree, but it is one in which the height of the left and right subtrees of any node in the tree differ by at most one. Okay, now that last bullet on the slide implies that we're going to use +1 and 0, -1. That is out of your book. I will actually recalculate with the actual heights of the tree, and I'll show you that when I give you an example. But in essence, we're going to look at balance factors, and balance factors are basically weighing the left subtree against the right subtree with respect to the height of each of these subtrees, and then determining if that exceeds 1. And if it does exceed 1, then we must rebalance the tree. So here's an AVL tree example. We're basically going to take a tree that begins as is shown in A, and then we're going to rebalance it by performing some rotations. And the point that we're trying to make here is that this does not give us a perfectly balanced tree, because we have the ability to have a delta of at least of no more than 1. But that means we could have a delta of 1 between the height of the left subtree and the height of the right subtree. It is not going to yield a perfectly balanced tree, but it will keep us from being so degenerate so that we're basically an order n data structure. There are actually 4 individual cases. 2 are symmetric with one another, where methods to return a tree into balance once we either insert or remove a node. So the first case here has a symmetric case, and I'll draw that out in a second. But this particular problem happens when we add a node to the right subtree of the right child. In other words, looking at it from the perspective of P, I've added a node to Q, which is P's right child, and I added it in the right subtree of Q. And so it turns out that there is an equal and symmetric case that looks like P and Q here, and I end up adding the node here, okay, rather than here. This is called the outer case because it happens in the same. It happens in the left subtree of the left child, or the right subtree of the right child. Right? So this is the right subtree of P's right child Q, and this is the left subtree here of P's left child Q. So if we add the node here, then that causes an imbalance that is going to be fixed with a single rotation, and that rotation is to basically rotate P and Q. So you notice that in this case, what we've done is we've rotated P and Q in this fashion so that now Q is the root here and P is its left child. Whereas when we started, P was the root and Q was its right child. And so this allows us to fix a with a single rotation, an imbalance brought about by this outer case. Now, the inner case is a little bit more involved, and it is also symmetric, and it involves adding a node to sort of the opposite side of the node that I'm looking at. So let's look at P. This imbalance came about by adding a node into the left subtree of the right child. So you notice if I go back here, we inserted into the right subtree of the right child, and the symmetric case is the left subtree of the left child. And in this particular case, though, it's either left of right subchild or right of the left subchild. And that is the symmetric case. And so what happens in this case is that the imbalance requires two rotations. It first requires, so the imbalance has taken place. So we take a look at P here. This is the right child of P. Q is the right child of P. And the imbalance is being caused by an insertion into the left child of Q, right? So since it's right and left, that requires a double rotation. The first rotation is to rotate Q with its child R in this case. And that rotation looks like this, giving us this picture. So whereas before Q was P's right child, now R is P's right child, okay? And then Q, which was previously the parent of R, is now Q is now the child of R. Now, this does not fix the problem. We still have an imbalance here. And so this further requires that we do another rotation, and that rotation is to rotate P with R, giving us the picture that you see on the right. And this will bring the tree back into balance. Now, that may not be immediately obvious, but hopefully when I go over the examples that I'm about to cover, this will make more sense. So the way we balance a tree then is to think about wherever the imbalance is happening. Think of that node P as being its own tree. And then you perform all the rotations below that particular level in the tree. And so there are a couple of interesting things here. So once we determine where the imbalance is, then it's going to be enough to fix the lowest the lowest imbalance in the tree. That will fix other imbalances above it. Okay, so again, I'll demonstrate that when we go over a concrete example. Now, when we delete a node from an AVL tree, we use the delete by copying method, which is what I went over when we talked about deleting nodes from a binary search tree. So this includes actually substituting a value into the place of the node you're quote unquote deleting, and actually deleting another node, either the rightmost of the left subtree or the leftmost of the right subtree. Okay, and as we perform this, remember, we're going to be processing these nodes with a recursive function. And so as the recursion unwinds, we're going to basically unwind all the way back from where the insertion or deletion took place, all the way back to the top of the tree, and we will fix any imbalance. We'll fix the first imbalance that we encounter, and that will actually repair any imbalances above it.